This is our October meeting of the Sacramento/Grass Valley SIFTI section. I'm Deame, by the way, for those who don't know me. I'll be your host and presenter, so I get to introduce myself. I'm going to be very complimentary. It's going to be a very long introduction.
Did you get your bio?
I'll have to go check on that. So I can figure out how to the screen. Okay, so a little bit of news on the SIFTI side before we get into the main presentation. We had our elections not too long ago. We usually take a break in the summertime, so some of you may not have seen this. The elections are in May, and we have a chairman with a one-year term, secretary treasurer with one-year term, and then 6 managers, 2-year terms, 3 every other year. The electees are as follows. Bob Huddleston on the far left is our chairman. Secretary Treasury, Mona Smothers, everybody knows Mona. And I'm one of the managers, newly elected or / appointed this past term. And I don't think any of the other managers are here, but we've got a good collection of people from the industry. We do have one open position. So I won't mention any names that left us. So if somebody is interested in,
you were left too.
You were ditched too.
ditched, yes, not just so anybody's interested in joining. Our past chair, Paul Turner, is also very instrumental. I put stars next to Bob and Mona's names as a reminder. They've been serving the SIFTI board for many, many years. I'd say 18.
18 for me, and
18 and
how much for you, Bob? 25.
immeasurable service to the group, but they've decided they'd like to not do it for a little while, maybe just a year off. I don't know. So we are looking for next May, for the next set of elections, a new chairman and secretary treasurer. If anyone is interested, please let us know, or recruit some of your friends. Interested. We don't have details on next month's meeting, but it is going to be an AI focus. It should be really interesting. Lots of discussions going on. We're just trying to nail down the who, what, when, and where. But AI, as you know, is a big topic, and it's moving into the broadcast space in some interesting ways. So for today's agenda, I'm going to give actually 3 little mini presentations. IPMX Demystified. So the first one is about the what is it? Where does it fit in the market? Kind of a high level overview. Why does it exist? And then the third one is more of a deep dive into the technical parts of it. How does it all work? So I decided to put a little mini networking 101 in between for people that might not be fully up to speed on video over IP. It's only 4 or 5 slides just to kind of set some context, so I don't put too many people to sleep when I get to the third section. So with that said, I will move on to my IPMX Demystified. Yep. Is okay. IPMX Demystified, and a little bit about me. So in our role, so I work for a company called Nextera Video, and our mission in life is to help broadcast and pro AV companies add IPMX or 2110 capabilities to their products quickly and easily. So that's kind of where I got my interest in all this and have been in it for many years. I've been participating in all the committees, back the early VSF committees that were doing the precursor to 2110 itself. And I'm currently active on the IPMX committee, which is VSF, Video Services Forum, is the group that manages that. And the number is TR10 if anybody cares about numbers. So if somebody asks what's the spec number for IPMX, it's VSF TR10. It isn't being done by SIFTI, it's being done by VSF. And SIFTI is happy with that. One of the reasons is we wanted to get fast time to market, and it's building on 2110, which has already been through the whole SIFTI vetting process. So it's more just, as I'll discuss in a minute, it's more just tailoring 2110 for the pro AV market. And as far as what our company does is we provide solutions and reference designs for manufacturers that want to add this to their products. Okay, so what is this IPMX? So in a nutshell, it's 2110 tuned for Pro AV. Kind of it. So 2110 works great in broadcast. It's the ubiquitous standard, but it's got some limitations. It expects there to be a PTP sync. It expects the whole system to be gen locked. It expects the video format not to change once you've connected A to B, a 720p camera to a monitor that can handle 720p. It doesn't expect you to change that source, whether it's a camera or a laptop, to another resolution. You have to reconnect it. In broadcast, you don't. You set everything up to the house standard and you let it rip. Well, in Pro AV, as you know, people come in a place like this, they drop in a laptop, plug it in, resolution's changing. You don't want to have to reroute your signals just because the resolution changed. So some of the things, the main capabilities, relaxed timing, so PTP is not required. If you've got it, it'll use it, and it's actually required to use it if you have it. Things like wall configuration, et cetera. And in addition to 2110 that supports uncompressed, IPMX does as well, but we've added the capability to do light compression and heavy compression, and it's actually open to multiple codecs, so it doesn't have to be limited to those two. Number three, importing different types of encryption. HDCP is an important thing in the Pro AV space, and as we'll discuss, there's also custom encryption that you can do. And finally, dynamic connections, which I talked about in the beginning. You can switch resolutions and it's happening. How can it be used? Well, I thought I'd give you a visual instead of a bunch of bullets. This is our demonstration at Infocom. This is an organization called AIMS, the Alliance for IP Media Solution, had a booth and invited in a lot of partners, such as ourselves and a few others, to really just demonstrate to end users and system integrators, how does this all play? What can I do with this IPMX thing? So it's a few examples. The top of the PTZ camera sitting on top as a kind of source that can put out IPMX compatible streams. Some of the consumers of that, there's an airport info monitor that you can barely see there that has your normal flight info, but it can have things like advertisements on the side. You can do windowing type functions. Pub multi-viewer, similarly, it's got some images. Maybe it's got the karaoke camera, and also it's got the menu board on the side. SDM, smart display module. You can get an IPMX enabled hardware module that'll slide into some large Pro AV monitors like 55-inch LCDs and video walls. There's companies that are making video wall processors, IPMX based, that will do all kinds of nice windows and things. You guys know a little bit about that, I think. Okay, so let's talk about AV over IP in general, now that you kind of know how it would be used. And so why do we need something different? There's solutions out there. Why do we need something different? Well, there's an increasing demand for it, and better quality and interoperability are kind of some big trends that have been asked for a lot by the consumer market. Scalability, the ability to go from HD to 4K and beyond. A lot of the LED displays are getting quite huge. I think the Sphere in Vegas is something like 16K by 16K. And that's all 2110, by the way. Increasing frame rates. And there's just a lot of confusion over the various options out there. So I'm going to try to walk through that and talk through some of the differences and pros and cons. It too many times. So the benefits, you get extended reach. You can do an HDMI distribution system, or an SDI is a little bit better, but HDMI, you've got cable limitations. You can't just connect it in a building that easily. You got to run a bunch of cable. But in IP, obviously, you can pull the network switch. Any place the network goes, you can have a sender receiver, assuming you provision for the bandwidth. And that can lower your infrastructure cost and give you flexibility. So current solutions for AV over IP. There's a very good system from Semtech that's been around for a while. That was an acquisition of a company called Aptovision. It's called SDVOE. VSRT has another system called NDI, which was an acquisition from Newtek. And Audinate has a system called Dante Video, which was an acquisition from Barco Silex. So you guys may remember the Silicon Excellence group of Barco that turned into Silex Technologies or something like that. So all interesting systems, but it goes a little deeper than that. There isn't just one NDI, there's 3 NDIs. There's HX2, HX3, high bandwidth, and they're all slightly different and they're not really all compatible with each other. Dante, you've got Dante A, which is A speed based, Dante H, which is HEVC based, Dante Ultra, which is J2K based. Again, not compatible with each other. They all solve needs of the industry, but it's a little confusing to customers. So the idea was, well, what if we could build a system that could span all of these requirements? That was interoperable, scalable, resolution independent, network speed independent, using industry validated codecs and built around open standards. So that was kind of the goal that AIMS and VSF set off 3-4 years ago to try to figure out, is there a better way to solve this problem? So I talked a little bit about AIMS. That's their logo, Alliance for IP Media Solutions. It's mostly a marketing organization. They do product management functionality for this IPMX spec. So they talk to customers, they write user stories, and bring in the requirements. And then the IPMX spec is managed by Video Services Forum, VSF. And what is IPMX? Well, it says it there. It's a set of open standards and specs allowing carriage of compressed and uncompressed video, audio, and ancillary data over IP networks for Pro AV applications. So here's the fun part, the chart. Well, what about all the other systems that are out there, and how does this compare and contrast to other systems? So we'll spend a little time on this chart. I've got a bunch of different criteria here on the left side, interfaces, codec, latency, et cetera. And then along the top, I've got some of the current solutions. So SDVOE, NDI, Dante AV Ultra, and IPMX on the far right. And I would say they all have pros and cons. They all have their use. I'm not trying to say, they all need to disappear and get replaced. So let's walk through some of these. So SDVOE is a very interesting system. It runs on a 10 gig interface with proprietary codec. It can do 4K P60. It can do higher resolutions with more channels, but with a single 10 gig is 4K P60. It can do uncompressed at 4K P30 because it's 10 gig, so you can squeeze in 6 gig worth of data on that uncompressed. Few lines of latency, HDCP is supported. Hardware, our friends at Semtech provide a nice ASIC, so I made that one green. That's kind of a big benefit of the SDVOE solutions. You can buy a low-cost ASIC. Low power, you can put it in wall plates, other things like that. So kind of the downsides, things like proprietary vendor specific control systems, much like some of the other ones. It does have probably some of the best quality out there, visually lossless, because it's a very light 1.4 to 1 compression ratio. But it comes at the cost of 10 gig. So if you got a 10 gig system and you're looking for great quality, it's a great choice. Moving down to the right, NDI. This is an MPEG-2 based codec. So older technology. It's kind of built to be able to run in software with very low CPU utilization. Also does 4K P60, subframe latency. Again, proprietary control system. Its downside is it's more of a we call it visually lossy. So it's a 30 to 1 compression over 1 gig. So not quite the quality, but if you care about low-cost CPU solutions, it's a great choice. Third choice, Dante AV Ultra. This is a higher end system. This uses that Barco Silex Calibri codec, which is a J2K variant. Similar to the IPMX codec, which is JPEG XS. They'll go up to 8K P60, subframe latency, HDCP, all the things that you'd like. FPGA core. Does have optional synchronization and near visually lossless, 14 to 1 over 1 gig. And IPMX is the last column. So what we try to do is just take the best from the other options and provide it in an open standard and provide more flexibility. So as you can see, Ethernet interfaces could be anything. It could be 1 gig, could be 100 gig, doesn't care, doesn't matter. It's just a protocol. You can run it over any speed you like. The codec, 3 choices currently. 2 that are published, uncompressed JPEG XS. We're busily working on the highly compressed, which will likely be HEVC, probably with an option for H.264. That's not published yet, but that's coming. And the idea is you have one standard for the transport built on 2110, and you just plug in the 3 different codecs that you might want: uncompressed, lightly compressed, highly compressed. So it allows you to cover a lot more range of applications and have some layer of compatibility. The resolution 32K by 32K, which is the 2110 limit. A few lines of latency, similar to SDVOE for the JPEG XS codec, the one that's most popular. One area where we tried to excel was in the security area. In addition to handling HDCP, it'll handle what we call PEP, Privacy Encryption Protocol, which means a custom codec. Sorry, not codec, a custom encryption system. So if you say, the problem with, there's two issues with HDCP. One is you have to pay for the licenses, which are expensive. You got to sign lots of contracts, pay for the keys. And 2, anybody that's got an HDCP receiver can decode it. Well, what if you want to protect your contents that just anybody can't decode it? Well, that's what PEP does. You can invent your own encryption. It's usually variants of standard encryption systems out there, AES encryptions, but you can have your own custom keys and protect it. We're getting a lot of interest in areas like medical and government military that have strong protection requirements. Available as FPGA cores or software. So there's a software solution and a hardware solution. There isn't an ASIC, so you could say that's the one downside. Can't get a super low cost ASIC, but it will fit in a $50 FPGA, which isn't too bad. Control system is an open standard. We think that's a big plus. So whether you're doing uncompressed, highly compressed, lightly compressed, it's the same open control system that the broadcast guys use. It's the 2110 NMOS control system. So you can see it all in one controller and manage multiple different subsystems from one control system. Optional synchronization and near visually lossless quality. Any questions on this so far? This is kind of the meat of the comparisons of where it fits in.
Didn't we have a guy who did a SMPTE presentation on NDI? Bob, do you remember that? Didn't he boast that they were an open standard versus the proprietary vendor specific? Because I remember, because obviously I'm the SimTech rep, and so I remember, feeling like he was separating those two. So do they have a different rendition of what open standard means?
That's a great question. A lot of people will say it's an open standard, and what they mean by that is that it's published. So when they say open standard, they mean open specification. You can download it, you can read it, you can look at it. That's fine, that's interesting, but it was still made by one company. It didn't have the industry validation. It didn't have any kind of oversight by some kind of authority, right? It kept it from being tied to a particular vendor. So that's really the big thing we're going for, is this open standard that's managed by VSF and promoted by SMPTE and JTNM and all the organizations. So it's not tied to a particular vendor. Cool. Yeah.
Thank you.
Good question.
Quick question too, sorry.
Yes, sir.
When you say under IPMX FPGA cores or software, is that comparable to like a DES, Dante embedded type of thing, where like a Dante, it's embedded in the software as opposed to the chip? Is that a similar type of application on the IPMX side?
Yeah, it's a similar solution. So as I mentioned, Dante's got a couple different flavors. So the Dante Ultra is the one I showed there because that's more the higher end of the market. But if you use the AVA, that uses simpler compression, or could use their A-Speed ASIC. So the AVA or the AVH, which is HEVC, could be done entirely in software on a PC. So that's what we're trying to do with IPMX as well, as say, if you're doing just one channel and you're doing 1 gig, it's HD, and you're kind of a medium speed, i3, i7 processor, you should be able to stream it. Or if you're doing lots of channels or 4K or uncompressed, that's when you would need a FPGA type solution.
And is it FPGA agnostic?
Yeah, it is. So I can only speak for our company. We offer cores for both Intel and AMD. I guess it's now Altera and AMD. So not Lattice, sorry, but so it's not 100% agnostic. If you're interested. Okay, why do we need open standards? We should, good segue, thank you, Mona. So we want to leverage the technical expertise of the entire industry. There's a lot of smart guys in different companies, but if you put all of them together, you can come up with ideal and optimal solutions for these problems. Reduce operational expenses by eliminating integration challenges, multi-vendor interop, plug and play. That's a big part of what we do is we get a lot of vendors together once or twice a year and do plug fest, make sure everything works, make sure everything's compatible, avoid IP dead ends. Horror stories during COVID about companies that had purchased X number of units from vendor A and they needed a few more, they couldn't get them, there was nothing compatible with it, they had to throw the whole system away and start over. So that's one of the benefits of being able, you can buy it from vendor A, B, C, D, and they all plug and play together. And I'll talk a little bit later about we're doing a logo program that makes it obvious to the end user, this will plug and play, because there are options, you know, compressed, uncompressed. We got to make it simple for the user to know what's going to plug into what. Okay, what are the key technologies? I mentioned it's based on 2110, yes, designed for high reliability, high scalability. So all this work that's been done over the past, 8 or 9 years to prove, moving lots of data over networks in a reliable way is leveraged. NMOS is the control system, plug and play discovery. When you plug in an IPMX device, it appears on the network, it pops up in their controller screen, and it'll even pop up in a little XY cross-point matrix grid. So you can see instantly, oh, look, I have a camera or a display or a laptop has come up, hit the cross-point button route perfect for me to be. And the optional codecs that are industry validated, currently JPEG XS and 265 on the way. So what's the status of the specifications? Good question. I asked it. The left side shows you the ones that are complete and published. I won't get into all these, but there's a section for control, media, and security. They're all published on the website. I'll show you where to find those in a second, but there's always more work to do. There's always more requests, add-on features. That's the blue stuff on the right. That's in development, things like USB, that's almost done. That's probably the highest priority. Info frames is ready to be published, and the PEP on the bottom is ready to be published. So those are all making good progress. Where do I find these? Well, go to vsf.tv and click on specifications, and here they are. And you can see there's quite a few of the green final ones. There's enough for the minimum subset of connection to allow you to do most basic systems out there. More things to come over the next couple of months. Okay, I talked a little bit about PTP early on, just kind of clarify what it is. PTP is like a network genlock, if you're familiar with the old style genlock. It allows you to specify timing and latency. It allows you to do precise synchronization between devices. And it is fully supported in IPMX, but it's up to the implementation. It's up to the system integrator to decide, do I want a PTP-enabled system or a non-PTP-enabled system? The JPEG XS codec, a little bit more detail here. Visually lossless at 10:1, meaning the average person cannot tell that it's not uncompressed. Well, 10:1 doesn't quite get you under 1 gig if it's 4K P60. So most systems run at 14:1. That's why we say near visually lossless, which means you got to look really close to be able to see any kind of artifacts. It looks very beautiful, just like the Semtech system does, and some of the other systems look amazing at 4K P60. Ultra low latency, which is important in a lot of the Pro AV markets, live presentations, etc. Just a few lines of latency, like tens of lines of latency. And small footprint for FPGA cores. We talked about x86 software codecs, and I didn't mention before, you can also do GPU-based software codecs that let you do more channels or run on lower speed processors, etc. Yes, the logo program. Yes, very important. If you buy a Blu-ray player or HD TV set, they have a nice little logo on each one of them that says HDMI. No question, the consumer knows I can buy these, I can plug in a cable from A to B, it's going to work. question about it. We need to do the same thing with IPMX. So we have a logo program underway. It's the IPMX logo, and it'll have some more words underneath it that haven't been finalized, but something like uncompressed. So, you know, A and B will talk together, or JPEG XS or HEVC. So probably 2 or 3 high-level logos, and some products will support multiple, so the customer knows what they're going to get. Full details will be rolled out in 2025. It'll probably be a self-certification program where you certify, you do everything on the checklist, you get to use the logo. Later on, we'll have some kind of formal certification, but that takes a little more time. Okay, talk a little bit about NMOS. We said it was plug and play. How does the plug and play work? Well, that's the job of NMOS. That's this open specification. It was developed by the Advanced Media Workflow Association. So you kind of got 3 groups or 4 groups really all working in parallel to make this IPMX thing happen. You got SMPTE, who provides the basis of the 2110. You got AIMS, it's figuring out the user requirements for Pro AV. You got VSF, that's doing the technical specs for the IPMX, and then you've got AMWA that's doing the software for the control. So it's an open specification. It's on the AMWA website. Anybody can see it and read it and download it, and it enables this plug and play operation. I think I have a picture that shows how plug and play works. Yes, I do right here. So let's say you've got a couple sources. It could be cameras, it could be laptops. You've got a display on the other side, and the cloud is just an IP switch. And you got a control panel. So those are the normal things you'd expect to have in any kind of video distribution system. The one new piece you have is number 1, which is the registry there. It's a little PC, a Nook PC is often used, or a server somewhere in the rack that has this file system. It's the registry. It keeps track of all the devices that are on the network. So what happens? Number 1, everybody powers up, and all these sources send a message to the registry without any user intervention. It's in registry. Here I am. I'm a Sony camera. I'm a Mac laptop. I'm a LG display. So he has that list. Then your control panel is constantly watching that using a couple different network technologies, so we can see that there's a change. The change gets sent to the control panel, and if this is a smart control panel with light up buttons, it can actually put the name of the device in there. If it's a GUI based one, it can do it very easily. So now the control panel has the name of all the sources and destinations. The user goes destination source take, like you would on any other control panel. And what happens under this behind the scenes is, you don't have this big cross-point switch like we had in SDI and HDMI. It's all done in the magic of IGMP, Internet Group Management Protocol. So the receiver tells the switch, he's currently receiving this the top source rather, he tells the switch, no, I don't want that top source anymore. It does an IGMP join, just a message. He sends a little message to the switch, Mr. Switch, please stop sending me source A and send me source B. And the switch does it. So you don't need this huge cross-point, expensive hardware box. It's just a regular IP switch. You can chain them together, get more channels. Life is good. Okay, so to kind of summarize this high-level presentation, Pro AV market is looking for this high-quality, cost-effective, interoperable solution that's got security, it's got flexibility that they need to handle anything that's thrown at them. IPMX gives you beautiful 4K over 1G. It's got multiple layers of security, and it leverages all the brightest minds in the industry from all these organizations, SMPTE, ISO, AES standards. There's not a lot of new invented parts. It's more taking the best from a lot of existing standards, pulling them together, publishing them, and then is not relying on a single vendor for core technology. And the good news is IPMX is gaining traction in Pro AV. I also mentioned medical, government, military, and finance. A lot of Wall Street adoptions, a lot of big installations have gone out of Wall Street. So that's the end of part 1. 30 minutes, not too bad. Okay, so what I'm going to do next, before I get into the gory details that might bore some of you, I'm going to give you some context of what the heck I'm talking about. A little 101 on networking. Maybe that will make it a little bit easier to absorb what we're going to do next. Okay, and I apologize for those of you that already know this. It'll be a review for you. That for those of you that don't know a lot about packetized video, hopefully this will make some sense so you get some context. So HDMI is a lot of stuff going on here. You've got this is an HDMI cable in the middle. You got lots of pins on that HDMI cable, lots of different buses doing lots of things. These TMDS, transmission minimized data signals going back and forth, carrying your video, your audio, your control block. You've got DDC channels that are providing information about the display. So you got all these different subsystems that are going on back and forth. A lot of hardware is involved to make all this happen. So, and it's a point-to-point system. So we're saying in IP, well, how do you kind of replace this? I want to put all this on an RJ45 cable, right? So you got to take all those buses and kind of run them down to a single cable, and you end up with something that's a lot simpler, right? You got a transmitter and a receiver and a switch in between. And that's really what IPMX is doing in a nutshell, is taking all those different interfaces and squeezing them down to this single wire. And as I mentioned, the benefits are, well, if you're in a switch, now you can go one to many. You don't need a monstrous switch to be able to send it everywhere. Well, so how do you send data over a network? So let's say I've got some data to be sent. Let's say it's just those characters I want to send. You have to break it up into packets. You can't just send one big stream forever, because there's things like error checks that go on in the switch, CRCs that are calculated. So step one, you break your data into these little packetized chunks. Step two, you add some headers in front of them so that the receiving device knows what you've done and what to expect. Is it audio coming? Is it video? Is it something else? So now I've got my data all separate, or is it a control signal, right? Now that I've got all this, I have to get it from A to B. And B needs to be able to understand, well, I've got two basic ways to get it from A to B. On the same switch with the same wire, there's two fundamental packetization structures, which are really just headers, right? You're still sending packets and data. I can either send it using the TCP method or the UDP method. TCP is what we use every day for email, web browsing. It's a guaranteed delivery method, and it's got handshaking. It's kind of like, this fax example here. You're sending acknowledgements back and forth. Hey, I sent you a couple bytes. Did you get that? Yes, I got it. Okay. Send me the next few. Yep, got those. Or, oh, no, I didn't get that. Retransmit. Send it again. Guaranteed delivery. Works perfect for files. Zero packet loss. Everybody's happy. Well, the problem is there's a lot of overhead with that. It doesn't really make sense for video, where you're really filling the network with data. So that's where we use UDP. And the UDP is a lot simpler. It's just, where is it coming from? Where is it going? And I'm blasting. It's fire and forget. It's just blasting the data. It's like a telegraph. You can't stop it. You can't say resend it. If you miss something, don't worry about it. And the next frame is coming along in another few milliseconds, and just take the next one. So so that's kind of the way that this IP packetization works. And in IPMX, we use the TCP part for HDCP when we're sending the keys back and forth, because that does need to be secure and guaranteed, and it's very low data rate. So it doesn't matter that it's not super efficient. But for everything else, the video, the audio, info frames, those use RTP packets, and a slight variant of that is RTCP for the sender reports. RTP stands for real-time protocol. RTCP stands for real-time control protocol. So those are kind of the basics of how those works. And then the last step is I want to send it someplace, so you have to give it an address. So you give it an IP address, which is called a multicast destination IP address, and a port. So you could actually send video, audio, ancillary info frames all to the same IP address, but you'd have to give them different ports so that the receiver can tell them apart. That's pretty much it. That's how we packetize data. So any questions about that? Is that kind of clear? You guys knew that stuff anyway. Okay, so now we'll get our hands a little bit dirty, and we'll jump into the details of the specification. What is this IPMX spec you speak of? How does it really work? Okay, so really what I'm just going to do is go through all the different dash numbers of the spec. As you guys that know 2110, you know there's a dash 20, 30, 40, 41 in IPMX. there is -1 through -14, and we all get the flavors there. So I'll walk through them one at a time and show you how this stuff works behind the scenes. As a reminder, what is IPMX? It's the extension of 2110. And they have a different set of key features here. It's similar to what I showed you before, but a key one that I didn't really highlight before is this top one, asynchronous senders. So in 2110, if you have a laptop and you want to connect it to a display, they're running different frame rates. And you're going to have a frame stick. You're going to have a variable delay to get from the sender to the receiver. We don't want that in the ProAV market, especially live presentations. You want the minimum possible delay. So one of the biggest things we put in IPMX is the ability to have an asynchronous sender without a frame sync, a laptop with no gen lock, no PTP. I can send my signal to a receiver, this display, for instance, and it'll lock to it with just a couple lines of latency. So that's a cool feature. Display synchronization for video walls. We talked about some of these things. USB and KVM support. I'll get into that a little bit later. Okay, so let's dive into the particular specs. I've shown you the list before. We'll go through these one at a time. It will let me go. So tier 10-0, simple little organization document, gives you an overview. This likes to automatically, thank you for advancing automatically. Tier 10-1 is the system timing and definitions. Somehow I got into auto advance.
I didn't want you to talk fast.
I don't have timings turned on this PowerPoint. It again. Another way if we have to. Okay, so -1, how do we handle asynchronous media? How do we handle PTP? How do we do the traffic shaping? And what's the SDP syntax? SDP, for those of you that don't know it, is a session description protocol. That's like a sidecar file that's used by the control system to tell the receiver what the format of the video is that it's expecting. As you may or may not know, 2110 is a self-describing stream. You can't just blast it and the receiver figures out what's there. It has to be told, by the way, it's 720p, it's 1080p. So that's what your SDP file, among other things, color space, etc., tells you everything you need to know about that. So the way it does the asynchronous media, that nice little trick I was telling you about, is it sends additional packets. It sends these things called RTCP sender reports. So it's another packet, another RTCP packet, in addition to the media packets that have information about the stream that's being sent, and it sends those every frame in the case of video. It also sends timing information that makes it easier for the receiver to figure out how all this works. For the PTP, if you don't have it, the senders must use an internal clock. If present, you must lock to it. And any device could be a Grandmaster. In 2110, you usually have a separate big, like $10,000 box that's your Grandmaster, but in IPMX, it's most common to have one of your devices just be elected as the Grandmaster or PTP leader, as we now call it, politically correct. Traffic shaping, we use the wide model, which is kind of the software sender model. So it allows, we just loosened up the timing so that it's easier for a receiver to work with either a software sender or a hardware sender. Hardware sender is going to be very diligent about sending packets. A software sender, not so much. We talked a little bit about the SDP file already. It's just got a little IPMX indicator so that the receiver knows what's happening. Okay, sender reports. What do they look like? Well, it's this orange stuff in the upper right, information about the sender, which includes some timestamps, and then it's the blue stuff, the blue-green stuff, which is the IPMX info block. And the info block, I'm going to go through a few of these. You're going to see the orange stuff stays the same, the blue stuff stays the same, IPMX tag, ref clock, media clock. What's mostly different is this green part, the media information block. So in the case of -1, the video is sent once per field of frame, the audio is sent every 10 milliseconds, and any ancillary data is it only needs a sender report when it's sent. Okay, so what does this really look like visually? So at the top, you've got RTP streams, and you got your video stream and your audio stream. That's a set of packets that are going out on a particular destination address. You send an additional set of packets from your sender that are RTP sender reports for video and audio that have this little data block in it that tells the receiver what to expect. So TR10-2 is uncompressed active video. Uncompressed active video is defined with this type of structure for the sender report on the it's video in RTP packets. The metadata comes in the SDP files. It can support 10-bit, 422, 444, 8-bit RGB, YCBCR. Typically, the clock is 90 kilohertz for both the media clock and the RTP, which is the packet clock. So simple for implementation. And it has the normal stuff on the right that you would expect. What do I need to tell a receiver so it can lock to my uncompressed video? Well, I got to tell it pixels, lines, frame rate, bits per pixel, aspect ratio, all those sorts of things over there. TR10-3 is your PCM digital audio. He's going to need the same kind of information. Remember, this is an extension of AES67, which is what's used in 2110 as well. Sample rates 48 kilohertz. You can also do 41 and 96, et cetera, et cetera. And what does the audio receiver need to know? Well, sample rate, sample size, channel count, packet time, measured sample rate. Of things. This guy to the side so you can see the rest of it. Okay, TR10-4. This is ancillary data. It wants to go one ahead. So this references SMPTE 2110-40, which is the ancillary stream in 40. HDCP. This is a fun one. How do we manage encrypted content in IPMX? Well, we decided not to try to do anything crazy like decrypt the data and then re-encrypt it. Really, we just want to be a transparent interconnection from the sender to the receiver. So you got a sender, he's spitting out encrypted content. You've got a receiver that expects this encrypted content. They're both kind of expecting everything on HDMI. Well, we're going to sneak in the middle and take that packet information, that the keys, for instance, and encapsulate them on IP and send them to and from the receiver. We're not touching them, we're not changing them. We're just creating a way to move them from the sender to the receiver without having to have an HDMI cable. And this is all validated through DCP guys. So it's all legal, it's all on the up and up. A lot of IP systems in the old days would just remove the encryption and then reapply it on the other end. That's not legal. This is a perfectly
Can you minimize the little image so you can see the whole slide?
Yeah, you're right. That doesn't even need to be up there. Answer is no.
Maybe scooch it over to the left then.
I put it. Oh, how would I do this? There we go. Yeah. Okay, excellent. Okay, so how does this all work compared to HDMI? Well, in HDMI, remember, we got more wires, right? You got your EMDS lines on the top, you carry your video and your audio, and then you have these separate lines that are I2C, this serial bus that goes back and forth that sends the data. So all we did in HDCP is we just put those serial lines and ran them over the VIP channel. So it's just a bridge. So that's why we call it HKEP, HDCP Key Exchange Protocol. Forward error correction. This is an interesting option that you can do in IPMX. It's not required. In 2110, most of you know it's usually a fully redundant system. It doesn't have to be, but in practice, there's two links. One goes down, it gets the packets from the other one. That's a little bit expensive for a Pro AV system. So how can you protect your packets? Well, one way to do it is with forward error correction. What does forward error correction do? It sends some extra packets in addition to the media packets that are redundant, so that a receiver can then do some clever math to recover those. look at some of those options here. So the way it does it is it calculates these extra packets by XORing each column. So I'm showing 16 rows and 2 columns. So XOR means exclusive OR. So it's a mathematical function of looking at all the pixel values that come in and exclusive ORing them and getting an answer and putting it in the bottom. And it sends that as a separate packet. And then it does it for the second column in this example and sends that as a second packet. So if you're missing any one packet in either column, it can reverse calculate the data that should have been in that packet. So for 1/16 overhead, you can now recover single event upsets. Well, one packet bad out of 16. If you get a string of them, 4 or 5 in a row, you're kind of screwed. But it's very good for typical kind of intermittent dropouts. It's built around the SMPTE 2022-5 spec for forward error correction. Again, we didn't invent anything new, just leverage the spec that's already there and just defined a couple different profiles. The two column 16 row for video, and then one, which is really just duplicating packets. Because if the data rate's so low, you might as well. Okay, 10-7 is compressed video. We already talked about uncompressed. Well, this is compressed. So this is in particularly the variable bit rate, which is 264 HEVC. Which references 2110-22, and the key information is in the green on the right. In addition to wanting to know the height and the width and the bits per pixel, you also need to know that bottom light green information, the codec info. Well, what is the codec? What's the profile? What's the level? So that the decoder can handle figuring this stuff out. 10-8 is the NMOS part of the spec that says you shall use NMOS. Use the particular 04s and 05 spec that's already written. And if you're JPEG XS, you comply to this DCP, which tells you how to inform the control system. By the way, I'm JPEG XS, so the control system doesn't try to connect a compressed sender to a JPEG XS receiver, because that's not going to work. So part of the plug and play is advertising these capabilities. Receiver synchronization. So this is a requirement that a link offset delay must be published. So we can support things like video walls or multi-viewers if you wanted to have it. Things that are published, minimum network delays and internal buffering. I'll jump to the picture. I don't want to just read you every line. So the visual representation here is I've got a few different senders here. They've got different delays. Their network delay could be fast on one, it could be medium on the other, could be slow on the next. What if we could tell the sender what these delays were and then distribute that to the receiver so everybody knew what the worst case delay was, then everybody can line themselves up to the worst case. And that's exactly what we do here. So with different network delays, you can have perfectly aligned video in IPMX. Tier 10-9, that's the system environment. That's equivalent to the, some of you may know the TR 1001 for 2110. It's kind of a general systems level description that says, here's how to build systems based on IPMX. Gives you lots of good implementation hints. 10-10 is the HDMI info frame. Unlike SDI that relies on ancillary data, HDMI relies on these info frames to carry things like gamut information, HDR information, etc. That is actually sent as a separate stream, but trying to make it easy for the user and the system integrator and the control system developer, instead of having it just be any old random stream at any address, we said, tell what, use the same address, the same multicast address, but just increment your port to media +3. And that way, you're guaranteed synchronization between these. You don't need to worry about somebody typing in the wrong address for the destination IP. Some additional information goes in the SDP. Remember the SDP session description protocol. That's the file that's sent to the receiver to tell it what to expect. This says, by the way, expect info frames. I'm sending that stream. Look at it, use it. We talked about variable bitrate compressed video a minute ago. This is the constant bitrate compressed video, CBR, which is what JPEG XS is, and the most common one used today. You have to put that little line in your SDP file. You have to follow this BCP on how to advertise to NMOS. And again, you have to give it the codec information in the lower right, in addition to all the other good stuff. AES3 audio. What if you want to send AES3, not just PCM audio? This gives you the details on how to do it, the different frequencies that are supported. 48 is required for senders and receivers. The others are optional. And AES3 can carry compressed audio, so that's why we have a codec information block in the lower right on this guy as well. So receiver gets everything he needs to know. PEP, so this is new. This didn't exist in 2110, Privacy Encryption Protocol. We mentioned that HDCP is one way to protect content, but not it's not private. If you want to use your own codec, you can do it. Any codec you like. And it uses a set of pre-shared keys on the sender and receiver. Very easy to implement, roll out. You don't have to pay anybody else for keys. And the SDP file gets another attribute called privacy, so the receiver knows that this is encrypted. The control system knows it's encrypted, and can make sure that senders and receivers are only connected if they all support this encryption capability.
And I'm sorry, I don't know if you said, is it in addition to HDCP or in replace of HDCP?
It could be both. Because remember, HDCP, all IPMX is doing is it's sending the keys back and forth. Typically, I would say it would be used as a replacement if you had non-protected content. So the reason HDCP exists is for Hollywood, right? People spend a lot of money making these movies. They don't want you to just copy them and distribute them. So if you're playing a movie, it's required to have HDCP protection, and likely that's all that you need because you don't care who's going to look at it. If you have your own custom content, HDCP won't be part of it. And if you want to encrypt it, you just implement your own system. So they could be used together, but very unlikely. More likely it would be an alternative. Okay, USB. This is another recent addition that's in finalization. USB devices to communicate, and again using TCP/IP, because a USB device could be a memory stick, and you don't want to be just blasting the data and saying, "Don't worry, you'll get it next frame." You want every bit to make it. You want it to be guaranteed. It's USB 2.0. It's any USB peripheral, any use case. Some pictures over there that shows the data communication and how the connection status is sent back and forth. I don't necessarily have to walk through those right now, but they're there for your reference. And here's what a system would look like. A typical example would be a KVM system. Let's say you had 3 different keyboard and mice, as are shown along the bottom, and one host PC, and you wanted to be able to switch between these. In the old days, you'd have either a cross-point matrix or a little switch on your desktop with a knob on it. You don't need that anymore. They're all connected to the IP network, and each of these devices are run through a gateway, which is just a piece of software that converts your clicks and your mouse moves and all that to packets that go over the network to the receiver. Device drivers on the receiver side are connected to another little piece of software up there. Now you've got a software-based KVM without needing any bulky boxes, and it's expandable to whatever's on your network. Very useful system for system level KVM. So summary here, 2110, it was a foundation for IPMX. It's proven in the broadcast space, and the whole point of this is to add a Pro AV layer to it to support the different capabilities that the Pro AV market needs. Not just Pro AV, medical, government, military, etc. It's an open specification, not tied to a single vendor. Specs are all available on the VSF website. You can download it. You can implement this yourself. You don't need to get orders from people like us if you don't want. You want to do it yourself. That's great. You've got all the information that you needed to implement a complete system. and there's quite a few products on the market today. This was February of last year, the ISE trade show in Barcelona. There's 3 or 4 transmitters and receivers, gateway devices on the left that are HDMI to IPMX. And there's a wall controller for LED video wall processor on the right. So there's probably coming up to about a dozen different devices available now. I expect to see a lot more at next year's ISE. It's catching on, and it looks like it's going to be a really useful addition to the Pro AV landscape.
Is the medical space like operating room type application?
Yeah, that's the big one. It's digital operating room and also endoscopy. So quite a bit of interest from the endoscopy market, because a lot of times they're using SDI today, and SDI doesn't have any kind of protection. So the HIPAA requirements, just sending a stream from the exam room to the doctor's office or the viewing room over unprotected SDI, they're getting a lot of heat about that. So they're looking for some way to grab that video, packetize it, encrypt it, and push it over the network. Then it doesn't matter where the doctor is. He could be in the lab, in his office, in the exam room with the patient. Anybody can get access to that content. Okay. Other questions?
I was curious, Jed, with SMPTE 2110, of course, the VSF generated the TRs and then looked at SMPTE to standardize those and creates the SMPTE standards.
Yeah.
So now VSF has a new group of TRs, a Pro AV market.
Mhm.
Is SMPTE going to standardize those, or is another organization going to standardize those, or is there a plan?
Yeah, great question. So in the 2110 days, the VSF kind of did a preliminary first pass, I guess, at defining what a broadcast video over IP system would look like, and produced a couple of technical recommendations, 04 or 05, I think they were, I don't remember the exact numbers, but they weren't really fully wrung out. They needed a bit more work. So it made sense to hand them over to SMPTE. Here's a basis. SMPTE spend a year and a half, build upon them, and flush everything out and do the interops and make sure the specs are solid. So that's what happened, and it made sense. When IPMX came along, there were kind of 2 paths we could go down. We said, well, we can build a whole new system that doesn't depend on that, and that's going to require pushing everything through SMPTE again, just to make sure nothing got left off or not thoroughly checked. Or we can build upon 2110 and just think of it as more of a profile of 2110 that's got a couple extra bells and whistles. And it's believed that at the time and confirmed through testing that we don't need that extra level of SMPTE validation. Extra work went into the specs. We spent a little more time on peer reviews. We sent them off to liaisons with other organizations like AMWA, and I think there's even a SMPTE liaison as well, EBU, et cetera, to review these. And then kind of the thing that tied it all together was we've been doing the interops. We've done 3 already, and there's another one coming up this February. So by being more diligent in the VSF about writing these specs, leveraging heavily on the technology that's already been SMPTE standardized and doing the interops, we think it can stop there. And there's not a need to spend another year and a half in SMPTE just to get a SMPTE number stamped on it.
Okay, this will really show my ignorance probably, but I'm curious, where does fiber fit in? Is there a use case for fiber in Pro AV? Is there already being implemented?
Yeah, good question. So there's a couple ways to use fiber. If you look at it just from the highest level, it's an alternative to copper that lets you go higher bandwidths and longer distances. So you could do it in SDI, right? There's such a thing as SDI over fiber. Embryonics makes some little modules.
We used to sell those.
Yeah. So it's like, let's not make a new protocol. Let's just give me longer length. And then the other place fiber is used is in IP network. So your home IP network is copper, it's the large 845 cables, but most businesses have fiber backbones because you might have 50 or 100 PCs on it. 1 gig is not enough. It's hard to run copper faster than you can get up to about 5 gig now, but it's and 10 at very short distances, and it's a little flaky. So most professional business networks are already fiber from what they call the backbone. So the thing that goes from switch A to switch B to switch C. Since video is super high bandwidth, 4K video uncompressed, is a little over 10 gigabits per second, it pretty much has to be fiber. So I would say every 99.999% of broadcast 2110 installations are fiber. Since IPMX is mostly used in the compressed mode, it does fit on the nice little copper RJ45. But as I mentioned the first slide, the comparison slide, if you're doing uncompressed IPMX or if you're doing like 100 channels of 1 gig, you would want to use fiber for that. It's just a infrastructure option. It has nothing to do with the spec. It's up to the system designer to use it. Yes, sir.
I'm curious how the USB recommendation interacts with some of the other ones, since you said the USB tunnel is using TCP/IP, you probably don't need the forward error correction, but can you still use the privacy or the PEP and NMOS for discovery, or?
Excellent question. So there are kind of groups of these that work together. The FVC is intended to really just work with the video and the audio. It's not intended to go on top of the USB. And the reason why is because the video and audio are these UDP packets that are send and forget, right? So those may need another layer of protection. Whereas USB is TCP/IP, it doesn't need another layer of protection. So you wouldn't use FEC with that. But NMOS applies to everything. The idea behind NMOS is publish, announce to this global registry all the capabilities of a sender or receiver. I've got USB, I don't have USB, I've got info frames, I'm doing AES, I'm doing compressed, etc.
Sorry about that. That wasn't you. The wall overheated.
That's why I was sitting down.
I answer.
Yeah.
The warning was it dimming? Yeah. And then, sorry, my apologies, but you got that one
I
away.
got this weird. It's tricky once you get to like 14 specs that
Redundancy.
they don't all talk about the exact same. They don't all necessarily work directly together. There's subsets that work together. It's a little even trickier even within NMOS. But the idea is that you'd have protection to the UDP streams that need it. Now, having said that, a lot of people were worried about doing non-redundant video over IP. Little more network 101. If you lose, look at the SDI world. If you have, let's say, an alpha particle comes in and it wipes out 1 bit of 1 pixel in an SDI world, what happens? Well, look on your screen, the luminance value or the chrominance value changes of 1 pixel changes by a tiny little amount, imperceptible. That's why SDI doesn't need to be redundant. It doesn't care. It's pretty resilient to alpha particles. What happens if 1 bit of if an alpha particle comes in and just changes 1 bit of a TCP or UDP packet? Well, the switch generates a checksum for every packet. And when it gets to the destination counts up all the bits. Does it match the checksum? No, it throws the whole packet away. So 1 little bit upset wipes out a whole packet. So what does that look like in the video? Dropout. Remember analog dropout? Dropout's back, woohoo. So that's what could happen. So a lot of people were worried about it. And that's why we just said, all right, everything's going to be redundant. The manufacturers and the customers all agreed, like, we'll just do redundant. I don't want to have even the slightest chance of a dropout. So when we started looking at IPMX, maybe we have to do FEC, right? We'll just recommend that people do FEC. So we talked to some of the network guys, and I asked, I was in the room with a Cisco guy, a Juniper guy, and a Arista guy, and I asked them all the same question. How often do you get these kind of network disruptions? Is this alpha particle thing? Is it real? Am I just imagining things? And he goes, well, we have counters in our switches, and they will count the amount of errors that happen. It's accumulated counter and single event upsets. Now that you get people obviously unplugging and plugging cables that can make a stream, but without a plug or unplug, how many errors do you get? All 3. They all gave me the same answer.
Mm-hmm.
And that's hundreds of facilities over 10 years, 0.0 errors.
But it could.
So it could happen.
Mhm.
So I'm not so hot on FEC anymore, especially in a Pro AV environment. one little dropout that may happen once a year, once every 50 years, probably not worth the extra expense of putting in the FEC logic. And then now you got a compatibility between to the receiver has to support the FEC, and the receivers today do not support FEC. Great
So another USB question, and it sounds like that's a pretty generic transport. You said it could even be a memory stick or something.
Yeah,
A lot of the other recommendations deal with compression. Are you specific to video or audio? Are you considering having codecs that would be able to compress arbitrary data on memory sticks or something rather than just moving that uncompressed?
Yeah, it's possible. You know, that's a layer that could be added at the application side. If you said, I want to move data from USB device 1 to device 2, the software can compress it before it sends it if it wanted to. So it didn't seem like that was something that needed to be part of the spec. If you could do it or not do it at the application layer. Transfer, anything you plug in, keyboard, USB, mouse, USB keyboard, USB stick.
I have two questions. Number one is what's the minimum specification for a receiver PT or a receiver node?
Okay.
And number two is if that specification is so low, or if that specification is low, what are the chances of it being supported on a mobile device like an iPad Pro or something with a little bit of a beefier processor, Wi-Fi 6E? Could we use a mobile device as a destination, as a receiver?
Yeah, great question. So remember 3 flavors of IPMX: uncompressed, JPEG XS, and the HEVC. Talk about all 3. The uncompressed, that's a pretty beefy PC. That's like a big Xeon server to be able to handle. It's mostly just doing the packet processing at that data rate. It's not so much the CPU crunching, it's DMAing the packets from the NIC into the main memory. That's a bit. Well, now there's some new NICs that are out from Mellanox that do a hardware-based DMA, and that's probably bringing it down. If you're willing to spend $1,000 for the NIC, now you can get it down into maybe an i7, type system. So that's uncompressed. Typically not used so much for software-based. More commonly, it's the JPEG XS variant because it is visually lossless in 1 gig. That is like, I've seen some demos with the i7, little NUC, fine for 1 channel of send or receive. The third layer is HEVC. One reason HEVC is so attractive in IPMX is because it has hardware assist. You can get FPGAs that have hardened HEVC encoder decoders in them, the Zinc family, for instance, from AMD. Intel is doing some stuff as well, Altera. But then you mentioned mobile phones. Guess what's in your mobile phone? An ASIC with a HEVC decoder. It's already there. So that's, yes, very intriguing options become available. A phone very likely would not be able to decode JPEG XS. It's going to try to do it all in software. I mean, they're getting pretty, but it's just not optimized for it. But if it's got a hardware ASIC core in there to do it, yeah, no problem.
Nice. Okay, great. Thank you.
It's up to Apple and Android or somebody to develop the stack that supports the IPMX protocol. As far as the number crunching, should be no problem.
So there are no follow-up question for that. There are no leaders in software development for like Apple or Android that are providing a shell for IPMX, right? Is that what we're saying?
Remember, not that I know of today. Remember, the spec is not really even started in earnest. We're just talking about it now. So I imagine that people that are participating in the spec development and others that get wind of it over the next few months will definitely head down that path. I won't be surprised to see that. Maybe more of a iPad type application, but sure, why not on your phone as well?
Thank you.
Other people?
Jed, do you, in Pro AV systems today that are using maybe one of those Ethernet standards you mentioned, NDI or so on, is Wi-Fi used?
Yes. So Wi-Fi is a little challenging because you get losses, right? You get drop packets, you get jitter, you get all kinds of things like that. So we actually have a customer that we're working closely with to do Wi-Fi 6 for a medical application. And it's looking feasible. I mean, we struggled for a while with them to try to come up with a robust error correction. So that's going to need something like a retransmit. So there's, I talked about two different kinds of error correction, I guess. I talked about FEC, which is sending extra packets, which works well if you have a few losses. I talked about TCP/IP, which is check every packet, which is too much overhead for video. There's a third alternative, which is a retransmit request, which is used in protocols like RIST and SRT, people that are pushing stuff to the cloud. So that would be kind of take the best of both worlds, send it like a fire hose, like UDP, but assume I'm going to get an error once every few seconds or minute, and just retransmit that one packet or those two packets. So it's looking feasible with that kind of technology. That's not governed by MT or VSF or IPMX or anything. It just assumes there's a good network there, and it's up to the user to, I guess, the developer to solve any packet drop problems.
I think maybe practical Pro AV systems today would just use wired Ethernet.
Yeah, I think
Share the experience.
99.9% wired today. Even the Wi-Fi stuff that we're experimenting with is point-to-point Wi-Fi. It's not just there's a lot of drop packets in the Wi-Fi system.
And hopefully it isn't that endoscopy,
Yeah.
is that right? Application of your medical.
Hey, what's the endoscopy? Let's see what's going on here. Yeah. Yes, Andy.
I understand that it's based on 2110. I guess my question is, if I have an existing 2110 system, I'll walk to a PTP Grandmaster redundant, and I wanted to add like an IPMX sender to that, like a video sender, for instance, and assuming my receiver could receive that format, it would register with my NMOS device. It wouldn't need to be any changes to the switch or anything else in the system to be able to make that happen.
Nope, switch is fine. The controller would need to be an IPMX compatible controller if you wanted to handle some of the extra metadata, I'll say, like I'll give you a simple example. If it's uncompressed IPMX, that just looks and smells like 2110. Any control system should be fine with it. It'll have a little IPMX thing in the SDP file. It might get ignored, but it doesn't really matter. If it's locked to PTP, it won't need the sender reports, right? Because remember, those are kind of the big differences. In IPMX, you'll get a sender report whether you want it or not. If you're PTP locked, you would just ignore it. And if you're using a codec, you'll get a little bit of information in your SDP file that says, by the way, this is JPEG XS, be prepared to decode it. If you're not using that, it'll work just fine. If you happen to have a device that's multilingual, your receiver that already knows IPMX, compressed, uncompressed, 2110, fine. You just, it would be good if your control system understood that, so that it would prevent the user from connecting, say, a compressed sender to an uncompressed receiver. Yep, great question. So yeah, they're kind of intended to all leverage the same ecosystem and use the controllers that are out there. And the controllers I've worked with, Matrox and who else? I think it was Imagine. These guys are all adding in, definitely Matrox. They're kind of pushing heavily on the IPMX adoption. So their controller definitely supports all these modes to make sure that you're connecting compatible devices together.
Expect companies that have their own proprietary ecosystems like Crestron or others that would forward to IPMX, or?
Yeah, so it's a great question, because it's always it's always in the best interest of a particular vendor for them to have a closed system. It's not in their customer's best interest, it's in their best interest. So, Crestron just did an announcement, they sold their millionth converter, their millionth gateway. And behind the scenes, it's running something very similar to JPEG XS, and it doesn't look that different than IPMX. It's just not an open standard. It's their standard. It's a closed proprietary standard, not even an open proprietary standard. So why would somebody like that do it? Well, if it was 5 years ago, they probably never do it because they've got their walled garden and they've locked people in and people are going to keep buying it. Well, that story I told you before, it was, they were one of the participants in that COVID tragedy where somebody had a bunch of units, 100+ units, and had to throw them all away because they needed 20 more. So that's one reason why they might consider it. What's the second reason they might consider it? We could say they've already saturated a big portion of the market with 1 million units. They're probably not going to sell 1 million more in the next couple of years, but they might sell 1 million replacement units. If oh darn, the industry now wants everything to be interoperable and compatible, we're just gonna have to build them another 1 million units to replace the ones we just sold. So that's what we expect would happen. No commitments from those big guys yet, either Restaurant or Extron have not committed to it, but they show up at all the events and they ask a lot of good questions. They're not defensive or antagonistic in any way. They're very receptive to what we're doing.
But that's DOE people.
We're friendly with those guys too. Definitely had quite a few conversations. So I think, in the end, the manufacturers want to sell product and generate revenue and make their customers happy. So if the end customers were saying, I don't really see any benefit to this, it'll solve itself, right? They'll keep buying proprietary solutions. If some of the end users, it doesn't have to take all of them, it just takes a subset to say, for my use case, I really need to be multi-vendor interoperable. We now have an option. They didn't have an option before. Now we have an option that allows them to open standards, multi-vendor, fully published system. There's still going to be a lot of people out there go, I'm happy with my NDI system or my SDVE system. It works for me. I've got an installed base. Don't expect another big supply crisis like we had during COVID. They're going to keep going. Right? I don't think it's going to replace anything. The intent is that it's going to allow the HDMI market to move into IP at a much faster rate, and kind of hopefully help everybody in the IT space, give the customers much more flexibility. Because the biggest thing, I talked about a lot of advantages of IP, but if you ask the 2110 guys, it wasn't cheaper, it was a lot harder, it took longer. Why did you do this? Like in a truck, for instance, and it's because of the nearly infinite size routing matrix you get. And in HDMI cross points and SDI cross points, it's big boxes, right, Bob? You built some really big boxes, multi-racks, and I ran out. I need one more input. Okay, I need double the system. It's not double the price. It's this X squared kind of exponential curve as your cross points grow. In IP, it isn't. You can do 2,000 by 2,000, 4,000 by 4,000. They have this, they call it a spine leaf architecture. So instead of having one big piece of hardware that every signal needs to come in and out of, it's a bunch of switches, and each switch has an uplink port that goes to a spine, they call it. So it's like this hierarchy of devices. So you could build a small 2110 or IPMX system with one switch. Switch has got 48 ports. You could do, let's say, 48 devices. Now I want 96 devices. I don't have to throw away that first switch. I just add another switch to it and a spine on top of it and connect them together. I need some more, add another one, add another one. And you need to make sure your spine has capacity, but the spines are usually built in modular ways, and they're usually running like 100 gig, for instance. So you're now taking all these, or 10 gig if it's only the IPMX world. You could take 10 or 25, probably more like 25. So a 25 gig leaf node, they call it, could handle roughly 25 endpoints on it. And that all gets concentrated on one 25 gig fiber, in this case, up to your spine switch. You can have as many of those 25s as you want. You could have 10 or 20 or 50. And if you exceed that, you can put another layer on top of that that's 100 gig. If you exceed that, like your big television studio, ABC built this big 10-story building, 2110, they're running 400 gig. And the switches keep getting faster and faster. So it's you're adding to your network, not throwing big chunks away. So that's the big reason people like IP.